Okay, good afternoon, everybody, and good morning to people who are in other time zones, especially those that are from the Far East, which is China, India, and whatever. Welcome to the 19th annual CMAS conference. You are now attending a combined session for machine learning and reduced form models. Developments and applications, and a second session that has been combined with it, which is remote sensing, sensor technology, and measurement studies. On behalf of Professor Jia Zheng of Tsinghua University and myself, Vinay Aneja, we welcome you to this session. And I hope this session will go till 3 o'clock this afternoon. We'll have plenty of time to robustly discuss any questions that participants or the speakers might have. And with that, I'm going to turn it over to Professor Jia Zheng. Jia, good morning to you, and it's all yours.
Thank you, Vinny. And hello, everyone. I'm Jia. So let's first welcome our presenters, and I will give you, every presenter have 2 minutes to give a brief introduction about yourself and your work. So first, maybe let's go to Dr. Yun-Su Cho.
Okay.
I'm not sure if I pronounced right or not. Yeah. So yeah, please.
Yeah, can you hear me?
Yes, I can hear you.
Okay, my name is Yun-Su Choi, who is the PI of University of Houston Air Quality Forecasting AI Group. And today, we actually propose the hybrid model between a CMAS and AI model to forecast the ozone concentration 2 weeks in advance. As you know, as a numerical modeler, everybody has the same problem. The first problem is, in order to focus 2 weeks, is timely very expensive, and also second problem is about like 30 days later, the accuracy of the forecasting system decreased rapidly. In order to overcome this difficulty, we designed the hybrid model. Basically, we are using the CMAS 1 day or 2-3 days forecasting result as the input, and for the AI modeling, that's how we can forecast the next 2 weeks in advance. Basically, we are using very comprehensive, like chemical or physically linking environment, reflected by the CMAS model. By doing complexity and let AI to figure out based on this one, we can forecast the 2 weeks in advance. Very interestingly, we are going to have in terms of index of agreement, and we maintain the accuracy of forecasting result over the 24-hour ozone forecasting in 2 weeks in advance. Still, we about 80% in a range. So this can be applied to NO2, NPM, and all other. Okay. So if you have some question, I'm going to take it and to do this in a meeting and after this one. Okay. That's
okay.
It.
Yeah, thank you, Dr. Cho. And hi, Vinny, shall we go to the first question first, or finish all the summary, then we go to the questions?
Okay, my suggestion would be, let's hear, we can go each as they have spoken, give them a time to answer at least the overarching question. So I'll move to it. Give me a second.
Okay.
Here we go. Dr. Choi, can you see the...
Okay, many questions. Okay.
Yeah.
Question number 1 only for you.
This is for only. Okay, how many days of CMAS simulation concentration were used, for predicting ozone in next 14 days? Okay, for our for this study, we only using one single day, the forecasting result. Based on this one, actually we forecast the next 2 weeks. It's still very efficiently captures the daily variation of the ozone. Have you used the previous day simulation from CMAS to correct the biases? Oh yeah, that's for the first day. We just using the bias correction, trying to improve the CMAS result. About like original performance of CMAS is about like a 70% accuracy. If we use the some bias correction, we can improve from 70 to a little bit more than 90%. Okay, that's the answer for my question.
Okay, thank you, Dr. Cho. Yeah, I think let's move. If you have further questions, and feel free to send your question to the section QA part. Okay, and let's move to the next presenter, Dr. Venchuka Avi. Dr. Avi, are you here?
Yep. Hello.
Hi, how are you?
Hey,
Welcome.
I'm doing well. I'm Dr. Sunny Ivy from UC Riverside. My talk was about our use of two machine learning algorithms to explore some of the meteorological sensitivities, and as that relates to ozone concentration or 8-hour hourly ozone in the South Coast Air Basin from 12 to 5 p.m. And we did this on a data set from 1994 to 2018 because there's been an issue in the South Coast with this reversal of the decline in 8-hour ozone design value. And so what we found is that temperature is the most explanatory variable for this, at least for meteorology. And that's also related to a greater frequency of high pressure systems over the basin.
Oh, okay. And we do have another a question for you, Dr. Ali. So the question is like, seems like there are no sensitivity to the input figure from 2004 to 2008, I mean 2009, 2013 from the analysis of a random forest model. So do you have any explanation about that from your slides, I think? Yeah, this question.
Yeah. So the way that we interpreted the Wilcoxon test is that if we have a p-value less than 0.05, that the, let me pull up the slide. I don't have it there. Yeah, so if it's less than 0.05, we consider that to be a different prediction than, say, the original prediction. And so we consider the removal of that variable to be significant for impacting the ozone prediction. So it looks like you and I have the opposite perspective of that slide, but we can talk about it later if you like.
Oh, sure, no problem. So I do have received another question from Hawla. So thank you, Hawla. So here's a question. On slide 19. So why is a possibility of detection of ozone extensions improving with time in your model? So does that say something about what drives the extensions on slide 19?
All right. Why is POD improving with time? Yeah. Okay, so what we think is happening is that if there's fewer number of exceedances, the model has an easier time with predicting exceedance versus non-exceedance. So we think so since the threshold is 0.7 and a good majority of the data are less than, 0.07 or 70 ppb, then it's easier to predict a non-extreme for these models. So as you get fewer and fewer exceedances, the model should perform a little bit better. Which, okay. Yeah, that kind of leads us to another issue issue of predicting exceedances.
Okay, we have more questions coming out. So, hi, David.
Yeah.
David have a question. Oh, if for all the AI. Okay.
Exactly.
Maybe we'll address that later. How about that? So,
Yeah, it's a good
let's finish
question.
all the AI preventers. Yeah.
Okay.
All right. Let's move to. Thank you, Dr. Avi. So let's move to the next person. Samuel Jones. So I don't think Dr. Jones gonna join us tonight. So unfortunately, but so let's move to Dr. Alper Arno. I know you, Doctor. You know, I know. Are you here? Hello.
He's there, but it seems to be muted.
Yeah. So I'm not sure how.
He should be able to unmute themselves. Or Brian, can you unmute him?
Hello. Dr. Anu, can you? Okay.
Oh, I'm so sorry. I didn't realize you were calling me. I'm
No
so
problem.
sorry.
Yeah, yeah, no problem.
Yes.
Welcome. Please, yeah, briefly.
I'm here.
Maybe within 2 minutes.
Sorry. Thank you. I apologize again. Sorry. Yes, okay. I am actually Alican Mertan from Istanbul Technical University. In our work, we try to forecast PM10 concentrations using deep learning techniques, and we compared a number of different architectures, and we did hyperparameter search for our problem, and that's basically it. Yeah. And we train our model using standard gradient descent algorithm, and we used mean squared error as a loss function. The input to all of our models are the same, and we feed our networks the previous PM10 concentrations and the features that we deducted from the date and time information of the measurements. Yeah.
Okay. Okay. Thank you.
Yeah,
So we have a question for you. Let me see. Okay, how to train the model and what the input figure on each model? Can you explain a little bit short, briefly?
Oh yeah, we trained the model using standard gradient descent algorithm with mean squared error. And the input consists of previous PM10 measurements and the date and time information, the features that we deducted from date and time information.
Okay, thank you. Yeah. All right. Okay, I think we finished all the preventer for the AI part, AI section. So maybe it's the open question for all of you. So if this is from Dr. David Wang, and the question is, it is known that the machine learning and deep learning is not good at extrapolation. So I wonder what you think about it. And another question is, I'm interested in knowing how much time they took in training step in your work. Okay, yeah, please.
Probably this is Yun Choi at the University of Houston, and I might try to respond to this question first. From my perspective, yes, and some for the extrapolation, then it's not good at extrapolation. But I do not, quite agree with it, because our group has been using, which is called like a partial CNN, and that's the one of deep learning technology to impute to the missing remote sensing data. For example, like AOD and some column data due to the many times missed by the some cloud. However, if we use a partial CNN And for example, and we can impute the modest AOD value then by using through the validation process, we almost like about like 80 or 90% accuracy. We can recover the all the like the missed data through the whatever extrapolation. And DNN kind of partial CNN is a little bit different because by showing many different images, so that's how like very efficiently they understand the how to extrapolation works. So my answer would be, and if we use the right DNA technology, then it is very good at extrapolation. And second question is, I'm interested in knowing how much time. Yeah, it depends on the size of the system. But for our cases, and we are covering all over the South Korea, there are domains about 300 different stations. Those data, our system is very simple and straightforward. So only takes like for training about 20 minutes, and then a real forecasting just to take less than 1 minute to cover all of the area. So again, in order to respond to second question, it depends what kind of system you set up. If you just set up a very heavy duty 3D CNN type of model, then of course in order to train it takes time. However, very simple, straightforward like a CNN model, it doesn't take a daytime. So I think in timing wise also like we efficiently target on our study. That's it from my side.
Thank you. Thank you.
Okay. There is a person in the audience, Praful Doda. He has offered to answer that question also. Praful, are you there?
Hello, hello, Vinay. I'm also a panelist in this session.
Okay. I apologize.
No worries. Actually, I just want to let everyone know that this question will be answered live instead of just typing the answer.
You can answer it now if you so wish.
Yeah, just like what the presenter already said, if you use good machine learning algorithm or deep learning algorithm, it is really good for prediction air pollutant concentrations as well. That's it. Thank you.
Thank you.
I'll make a comment on an extrapolation.
Sure, please go ahead.
So in the context that we're using machine learning, I do think that we will miss exceptional events. But for the purposes of state implementation planning, I'm not a regulator, but I don't think they're interested in trends as it relates to exceptional events anyway. So I think what we're trying to do in regard to modeling exceedances should be pretty effective aside from wildfires and exceptional events.
Thank you. So any comments from Dr. Luca? No? Okay, and so yeah, please send your comment if you like to the last question as well. So let's move to the remote sensing section. The first presenter, let me see, is Dr. Chahano.
Yeah.
Yeah. Are you here, Dr. Chahono? Hello.
Oh yeah. Good morning.
Hi. Good morning. Welcome. Yeah. Please.
Because yeah, today is Wednesday.
Yeah.
Yeah. Yeah. I answered its question. Actually, I did wet diffusion samples in Indonesia were collected using rainwater samples in several cities, namely Serpong, Bandung, Jakarta, Kota Abang, and Maros. in each set, measurement of rainwater precipitation, pH, electroconductivity, and analysis of ions were performed. And also the deposition measurement was conducted using filter pack method to determine the particulate component of NO3 minus nitrates, SO4 minus 2, ion sulfate, and others, and gas of SO2, HNO3, and H3, and HCl. The air is inhaled using a pump with a flow rate of 1 liter per minute for 14 days continuously, and then passed into a 4-stage filter pack, whereas in each filter set is specifically absorbs its chemical components. Yes, enough. Thank you.
Oh, thank you. I have a question for you. Do you have any measurement for like particles component, like sulfate or nitrate?
Yeah, the other it's NO3 and it's 3 ammoniac and it's Cl.
Okay.
This we measurement for deposition.
Okay.
Yeah.
Okay. Thank you.
Yeah. Very
Yeah. Okay. Yeah. If anyone have questions for Dr. Trahono, please send it to the live section. Okay. Let's move to the next presenter, Dr. Fernando Campo. Dr.
Yes, sir. Here I am.
Yeah. Welcome. Yeah, please.
Thank you. Thank you very much for the opportunity.
So you have 2 minutes to summarize your work and introduce yourself a little bit.
Okay,
Yes.
excellent. Well, my name is Fernando Campo. I am a PhD student at the Laboratory of Air Quality Control, the university in Florianopolis. And well, as a quick summary, in the presentation, I presented the preliminary results of deploying 2 low-cost air sensor platforms that our team developed. And the platforms consisted of a mobile node and a fixed node. And we were looking forward to performing some preliminary analysis of our the prototypes we developed, because since we, at least for now, we don't have access to regulatory instruments and stations. So we came out with that solution as a preliminary evaluation of the prototypes. And well, we conducted measurements for 3 months with a fixed monitor. And with the mobile monitor, we performed some measurements during 4 weeks. And with the mobile monitors, we took air quality readings on streets and residential areas during different days of the week and different hours of the day. And we observed that the outputs of the sensors, both sensors we used, which were a sensor from SPECI, a SPEC sensor, and AlphaSense, we observed that the outputs of those sensors were very noisy, and the responses were poorly correlated. And we also observed that there was a high correlation between the daily variation of relative humidity and the output of the SPEC sensor. And on the other hand, we observed that the AlphaSense apparently was able to detect an increase in the air pollution level during rush hours. Well, that's basically the summary, what we did.
Thank you, Dr. Campbell. So I have a question for you. Is that possible to correct the sensor result by eliminating the RH impacts?
Yes, absolutely. We tried to approach to that by removing the daily pattern of the responses, because we saw that the SPEC sensor, its response was very similar. Its behavior was very similar to the relative humidity. So we we remove that behavior in order to see if it was measuring something else beyond the relative humidity, right? But we didn't find very interesting results because the output of the sensor was very noisy, in particular the SPEC sensor. And well, we didn't move forward to more advanced methods because since it was so noisy, we thought it didn't work. It wasn't very sensitive to the response. But yes, absolutely. Removing the relative humidity impacts, the measurements would be much better. That's it.
Great. Thank you so much for your answer. Yeah.
Thank you. Thank you very much.
Sure. Thank you. Okay. Now let's move to the next presenter, Dr. Chen Peng Yang. Dr. Chen, are you here? Hi.
Hi, thanks. Can you hear me?
Yeah, I can hear you.
Oh, thanks. Hi, everyone. My name is Pei Yan Chen from UA Huntsville. So I'm currently still a PhD student. And I would like to introduce briefly talk about the presentation we had. So basically, we tried to assimilate a cloud observation product from the geostationary satellite GOES 13 into a WRF smoke CMAS modeling framework. Our results showed improved model cloud placement and also solar radiation. And these improvements have changed mainly the biogenic VOC emissions and also the photochemical reaction rates. And also some of the model dynamics as well. And so those have kind of improved the daytime ozone performance in the CMAS simulation. The daytime ozone is the overestimation in daytime ozone is reduced by about 1 ppb of the coolness, and then the daytime maximum is reduced by about 50%. And we noticed the improvements are highest in the southeast and the deep south states, like where there are intense biogenic VOC emissions because there are just a lot of vegetation, and also here we have a kind of cloud activities going on. So that's the summary.
Thank you, Dr. Chen. So we have two questions for you. And the first one is, is there any reason to explain they have worse performance when you're doing the cloud simulation on PX model compared to the NOAA model? So do you have any thought about it?
Well, maybe I need to do a little clarification. So when we compared the performance between PlumView and NOAA schemes, the performance is we mentioned in slides is the cloud agreement index. So the improvements in PlumView is a little bit worse. I mean, it doesn't have as much as improvements in PlumView than the NOAA, but when we compare for example, radiation and also chemistry fields, the PlumView still outperforms the NOAA scheme. So, and okay. The reason actually, I'm still not quite sure about it. It might be some competition between the cloud simulation technique and also the PlumView, dense surface model when there soil moisture and temperature adjustment going on. So that might kind of reduce the improvements with PlumView.
Okay, thank you. Yeah. The second question is, can you define the cloud agreement index and which cloud dataset is used? For example, wearable or infrared. And I think the matters because the cloud, there are different cloud types captured differently in each product, so have varying effects on the photolysis rates.
Yeah,
So
thanks. That's a good question. So the cloud agreement index is actually a measure of how well the model clouds agrees with the GOES cloud observation. So if the model, for example, in each pixel of the model, if the pixel is clear and the GOES observes the clear sky, or both of them are cloudy, then we set the cloud agreement as 1. Otherwise, I mean, if the model is clear, but the GOES is cloudy or vice versa, then it's going to be 0. And that's the idea of how we count this cloud agreement index. And then for the data set, it's actually derived here at UH in the collaboration with NASA Sport. So it used the GOES 13 visible band image only. I mean, I believe it's on slide 2, there is a paper, White et al. 2018. He talked a lot about the performance of that cloud assimilation into meteorology fields. So maybe you can take a look on that.
okay, thank you, Dr.
Yeah.
Chen. Thank you
Thanks.
for addressing questions. All right, let's move to the next presenter, Dr. Jin Jin Wang.
Hello, everyone. I'm a PhD student in Department of Chemical Engineering at the University of Utah. And for this conference, our research school is aiming to understanding the physical processes impacting AOD remote sensing uncertainties. So we use a very conceptual way and develop a simplified radiative transfer model with a propagation of error approach to identify how satellite AOD retrieval uncertainties associated with surface albedo and prescribed aerosol properties. Also, we expand the critical surface albedo concept to a more general concept about critical critical asymmetry parameter and critical single scattering albedo. In these ways, we can analyze the errors in satellite AOD retrievals in terms of critical values, so that we suggest we should consider these critical values in our next generation of satellite AOD products to improve our satellite AOD products performances. Yeah, this is us work.
Thank you, Dr. Huang. And we have a question for you. Does the calculation of those critical values work for AOD larger than 0.1? Since in most cases in developing country, the AOD is way larger than that value. So can you address that question, please?
Yeah, this is our model's limitations actually, because our model only considers single scattering assumption. So this means if the AOD is way larger than 0.1, our model cannot do such a calculations. But we compare our work, our very simplified radiative transfer model, to some previous work that used a 6S radiative transfer model. And the results shows that we have a very similar trends about how AOD uncertainties behavior under the critical surface albedo, critical single scattering albedo, and the critical symmetry parameter. So I think our model gives an initial understanding about the physical processes impacting AOD uncertainties. Yeah.
Okay, great. Thank you, Dr. Huang. Okay, and Our next presenter, Dr. Hossein Hajpo.
Hello, do you
Hi.
hear me? Hello.
Yeah, I can.
Yeah, thank you. Good night and good morning to everybody in the room. I'm Hossein Khajapour. I'm a researcher at Energy Engineering Department of Sharif University of Technology in Tehran, Iran. Our work was we intended to see how important could be the effect of agricultural waste burning in air pollution in Tehran. We used the remote sensing techniques for identifying the sources of agricultural waste burning in around the city. We have checked the thermal anomalies around the city, and then we identified the most frequent, thermal anomalies, and then we identified which one of them are related to agricultural waste burning. Then we have checked what could be the path for distribution of the pollutants which are being emitted from those sources, and we have identified that among the 5 main agricultural waste burning sources in the south of the city, some of them are happening in parts of the year which the path of the pollutants goes over the city. We have also checked the changes in the concentration in the nearby air quality monitoring stations in the city, and we have identified a slight increase in the PM2.5 concentrations when right after the burning of the waste in those sources. In general, we have shown that the estimates of the amount of the primary PM2.5 emissions from these sources could be as high as 5% of the total primary emissions in the city. And also we have shown that these emission sources could be effective in the observed concentrations in the city when they are being burned. So they could not be neglected in the current emission inventory, official emission inventory of Tehran. It is mostly the agricultural waste burning is neglected because it is somehow around the city, not inside, and therefore they are understood that not very effective on the air pollution of the city. This was a general overview of what we have done. We have done in our research work. I'm available if there are any questions.
Oh, thank you, Dr. Hanapo. So we have a question for you. Are there any control measures for agricultural waste burning in Tehran?
Yes, there is a national, let's say, Clean Air Act in Iran, which penalizes any considerable air polluting activity. That also includes the agricultural waste burning. But in Tehran or in cities which agricultural activities are not very dominant, then it is more than a recommendation than an obligation. But in cities other than Tehran, such as in Khuzestan or other provinces, we can see that it is taken more seriously, especially in the days which there is a high concentrations of the pollutants, then it is more controlled.
Thank you. Appreciate your answer. Yeah. Thank you. Okay, I think our next presenter, Dr. Maria Makarova, she cannot join us tonight, unfortunately. So let's move to the last presenter, Dr. Junhua Zhang.
Hello.
Doctor.
Yeah, I'm here. Thank you. So for my presentation, I'm going to talk about we examined the modest difference indexing product for air quality modeling. And I'm a scientist in the Air Quality Research Division of Environment Canada. And we use different index to calculate biogenic emissions and also for surface processes like dry deposition. So mainly in North America, basically we have 2 sets of data sets that being widely used for air quality modeling for estimating biogenic emissions. The first one is biogenic emissions land use database. build a database. And we use this database for our Canadian GenMac model. The second one is modest different index product, which is used by, for example, Megan model for biogenic emissions. And we look at the two datasets and we saw limitations for both. For example, for the version 4 of the build database, and it only uses 4 leaf-area index values for various vegetation species. For example, it used 7 for all the spruce and firs, use 5 for all the broadleaf trees, 3 for all the pines, and actually 0 is used for crops. So it's very broad value. It's not a detailed value for various regions or various vegetation species. And it also only has winter and summer fraction, does not have a seasonal variation. So for the modest leaf-area index product, on the other hand, it has monthly, even final, actually it has 8-day leaf-area index product. So we can easily build a monthly leaf-area index product to use in the model. But the models also have some limitations. And in my presentation, I showed that one is that for the winter time, for the boreal forest in northern Canada, actually leaf-area index value is very low. And also, models does not have a retrieval for urban areas. Therefore, if we use the modest leaf-area index for fine resolution urban study, and biogenic emissions will be dramatically underestimated. So again, in my presentation, I just examined those issues and features and proposed approach to get a reasonable leaf-area index by combining the build for and modest product to get a seasonal variation, for example, and a reasonable leaf-area index value for air quality modeling, mainly for North America. That's all for my summary. Thank you.
Thank you, Dr. Zhang. We have 2 questions for you. First one is any suggestion to improve LAI data for regions where the model of the BELD model is not available, like in Asia, we cannot use that model. So do you have any suggestions?
Yeah, this is a very good question. Actually, I'm thinking about it as well. Even for North America, there is no about data for Alaska, for example. So actually, I think maybe still use modest data. And from the modest land use data, it has some land use category or land classification. For example, boreal forest, evergreen forest in northern Russia. And if that is available, you can use, based on my presentation, there is a monthly variation. For example, you can use 80% of a summer leaf-area index for winter. Should be reasonable value. But on the other hand, for area with mixed forest, it's difficult. And the only way I think to get a reasonable value is based on the local knowledge or local land cover database to modify the modest data.
Okay, thank you. Our second question is because modest LAI appears to be anomalous low in urban area, is it fair to say that isotope emission in urban area in the model are underestimated compared to more rural areas?
Yes, I think for this question, the answer is yes, if you use the modest data directly without any modification, yes.
Okay, thank you so much for addressing the question.
Thank you. Yeah.
Okay, I think we finished all the presenter and the questions, and we have summaries. So is there any open questions from the audience? You can feel free to submit any question to our presenters. We still have around 40 minutes.
Dr. Jia, I have a question for Dr. Kajapur, if he is. Okay. My question to you is twofold. One, Hussein, is what kind of agricultural biomass burning activities take place surrounding Tehran? And two, the question that was raised initially is, are there any policies in place to minimize or mitigate these emissions at the source itself?
Thank you for your questions. As far as I know, around Tehran, mainly the, let's say, vegetable products are being produced, and therefore, for instance, the fruits are not very growing easily in the climate around Tehran. They are mostly imported to the city. But for some sorts of vegetables, they are being produced around the city. And you know, if you're familiar with the Iranian diet, it is very common that they use different types of raw vegetables in their daily dish. So this is to the best of my knowledge. And as you know, in Tehran currently, around Tehran, because of the water scarcity issues, the greenhouse cultivation is being expanded very much more. And in the eastern part of the Tehran province, there are huge lands allocated for greenhouse cultivations. But in south of Tehran, which we have studied, it is mostly just primary vegetables which are used daily in the city. And regarding your second question, actually the main sources of air pollution in Tehran are mobile sources, as it is in many megacities in the developing world, and also then there are some, depending on the coverage of your emission inventory, it could be the industrial activities. Actually, the agricultural waste burning is very, minor in comparison to them. It is estimated that more than 50% of the primary emissions is coming from the mobile sources in the city, and the agricultural lands are quite far from the city, so there are much less sensitivity to them. As I said, only in polluted days during the year, the environmental office of the city is taking more care of any sort of emissions around the city, and then in those days there are more controlled over the agricultural activities and farmers around the city. Also, there is another source which we have studied in our report, in our presentation, is the central waste management complex in the south of Tehran, which there is a very, a small amount of the waste burning, municipal waste burning in the city, but it is also quite more controlled, especially in the polluted days. I hope I have answered to your question. Most welcome.
Thank you. Okay, we receive another question for Dr. Zhang. So the question is, how important are biogenic VOC emissions in wintertime? For wolf awful output LAI, how different is from the motive of about derived LAI?
Okay, yeah, again, this is a good question. Actually, for the wintertime biogenic VOC emissions, it probably is not important. I think for the wintertime, the leaf area index will be still important for the land surface process. For example, the dry deposition. You know, if you have a low leaf area index, it will definitely impact the dry deposition for the wintertime. Based on my comparison, actually the leaf area index derived from Belt 4 actually is quite different from MODIS, for example, for the boreal forest in Canada for the summertime. Again, I just mentioned that the 7 is used for the all the spruce and the pines, and in Belt 4, actually for northern Canada, the value around about 5-ish, 6-ish. But from the MODIS, if I remember correctly, is about 3 to 4. There's 1 to 2 difference for the value. Yes, there is some difference between them.
Okay, thank you, Dr. Zhang. So, yeah. So, any more questions? We still have around 9 minutes for this section.
Dr. Jia, there is a question on chat, and if you like, I can read it to the panelists. And it says, regarding drought, DiMattillo et al. 2019 ESNT showed that isoprene declined during the severe drought period in Central Valley, California, 2014-2015. The same is most likely occurring in the South Coast. Would anybody like to comment on it?
Okay, I believe that's a question for me.
Yes.
Okay,
But I'm open to anybody else.
Oh, okay, that's cool with me too.
Go ahead, Suni.
Oh, okay. Yeah, so that paper is really nice. I use it as a reference to understand all of these different drivers at the same time that may be affecting ozone. And as you can see, if you guys have pulled up the paper, at the early drought from 2010 to 2014, there's a slight reduction in isoprene, but during the severe drought period from 14 to 15, that's when you start to see really, really high reductions. I think post 2016, we had those atmospheric river events along the West Coast from 2016 to 2017. And so it'll be interesting to see how isoprene recovered during that period. However, I don't have access to those data.
Okay, thank you, Dr. Fanny. So we have another question for Dr. Cho. So how many days do you use to train the model? Do you train it for different phenotypic conditions?
Oh, okay. It seems like a question for me. And for this study, we have used about 30 years, 30 years, historical data. So for ozone and the reason to why we are using 3 years, and even though we have a 10 years, but it turns out about 30 years kind of historical like a training that's good enough to understand what's going on regarding ozone. Of course, like some other tracer might be PM and NO2 we are also working on, but I think about like a 30 years one very pretty well, captures the phenomena over there, variation and changes, from our like AI modeling system. And another question would be the, what is the second? Oh, different synaptic condition. Yeah, yes and no, it depends. And for our like a PM 2.5 forecasting system that we did actually use a different system or different synaptic condition. That's how somehow the model, an AI model is better, better, capturing the particularly high value of the PM and something. So it depends what are you targeting at. But yeah, you're right that if we just using a different, we will consider a different synaptic condition, and sometimes the some specific condition, the system better trained. But one problem is the basically AI needs the big data, right? So AI is supposed to experience and learn many different kind of experience. So actually, our groups in AI system are two different. The first one is generalized in an AI model, one single AI model using a big data, trying to make the cover in all other scenario. But in that case, of course, some specific synaptic condition is not good, well trained. However, many big data, that's how the AI model become better and better. And another one, as you mentioned, that for particularly for the PM, those kind of a study, that we are using some like a different season and different synaptic condition. That's how we can make our model very efficiently. We just efficiently guide, wisely guide the AI model to figure it out. Because still, even though we call like a big data, but that's only like a 30 years data, 10 years data, right? So not a 100 years, 1,000 years data at all. So that's why we need some specialized the AI modeling system. We should have to. So we have a two different strategy to do this one.
Okay, thank you, Dr. Chou. Oh, okay. We have 3 minutes left, so probably maybe the last question if you have for all. Any more questions?
From the audience or the
Yeah,
participants?
Yeah. Okay. Yeah, we have a question for Dr. Chou. And the question is, can you comment on the use of machine learning to accurately predict primary and secondary pollutants?
Second, what is your question again?
Oh, the question is, can you give some comments on the use of machine learning, maybe to improve the prediction for primary or secondary pollutants?
Oh, okay. So yeah, as long as you have the, we have the big data, so which means some like experimentally, observe the data, right? Some true value we need to have. However, sometimes like, for example, like one of like secondary like SOA components, usually we do not have the big data outside, right? In that case. But still in that case, at least like if we like refer the modeling data is like a true value, then we can train the AI modeling too. So this is today only I just showed the forecasting, the some specific pollutant. However, this in AI model can be used to inside of a model, numerical model. Sometimes numerically very time consuming module can be replaced by using AI model. One of our in a project we are working on today. So actually we replace some like a very time consuming module inside of a CMAC or like a WAP model. We just replace the timely very cheap like a module, but similarly the capacity but timely very cheap. So, and also like as long as the big data is available, as long as some observation data is available, then primary, secondary doesn't really matter, because the model, AI model also, consider all different kind of detailed chemistry and physics. And if we use the like a CMAC output or CMAC input, we are gonna use it. Then it's a lot AI somehow understand the comprehensible chemistry and physics too. So it depends, and at a certain level, yeah, I'm quite sure. Then how you can just organize and set up the AI model. That's how we can see what's going on. Even like very detailed, understand the very detailed like chemistry and physics. I think so. So as long as sometimes that input will be from the model, from CMAC or some observation, something. It depends on often whatever like you just target and a pollutant if you have, then we can set up. And sometimes the good thing is for the AI model is we can use the all different kind of input for the AI model. Sometimes observation, sometimes modeling. So that's a good thing. so numerical and some numerical, so that's how the, so AI model is very, very easily like applied actually. Okay.
Thank you. Thank you, Dr. Cho. Really appreciate your answer. All right, I think we're almost there. And Vanny, do you like to give us a conclusion? Thank you.
Well, this brings us to the end of the session. I would like to thank all the panelists for sharing their wonderful research, remote as it might be. Hopefully next year we might all be in person together. But that being said, I would like to thank all the panelists. Equally importantly, I'd like to thank the entire audience for participating and being a part of this process. And lastly, I'd like to thank Sarah Farrell, who very diligently orchestrate this entire thing. So Sarah, thanks a lot. And on behalf of Dr. Jia Zheng, and myself, I'd like to thank you all and have a wonderful evening and goodbye.
Thank you. Bye.
Thank you. Thank you, Prof. Anaja. Thank you, Bian.
Thank you for the organization.
Thank you, everyone.
Thank you.